Ladies and gentlemen, for the very last live demonstration of the afternoon, we are very pleased to welcome Thermwood to the spotlight. Thermwood has been the market and technology leader in large format additive manufacturing since 2016, thanks to their innovative large-scale additive manufacturing systems. To present Thermwood's game-changing technology, we are very pleased to welcome Scott VAAL, who is the LSAM product manager, and Dr. Eduardo BAROCIO, who is the assistant director of additive manufacturing at Purdue University. Thank you so much, Scott and Eduardo, and for coming to see us once again. The stage is yours.
Thank you. Well, hello and welcome, everybody. My name is Scott VAAL, and I am the LSAM product manager for Thermwood Corporation. We're pleased to have the LSAM 510 additive printer printing live for you here today. And it happens to be one of the smallest models that we build. LSAM comes, if you're not already obvious, LSAM is Thermwood's large-scale additive manufacturing system for thermoplastic polymers. It comes in a broad range of sizes and configurations, up to 15 foot by 40 foot by 5 foot, or 4.6 meters by 12.2 meters by 1.5 meters. The LSAM comes in print-only versions, and it has versions that have print and a 5-axis CNC router head on the same machine. In fact, some of our models can actually print and run the router at the exact same time. So, of course, today we want to talk about large-scale 3D printing, but more specifically about large-scale 3D printing with high-temperature materials suitable for autoclave tooling applications. In fact, that's what we're printing live for you here today. With help from the research team at the LSAM Research Laboratory at Purdue University, a full-circle demonstration and detailed study was performed on an LSAM autoclave tool for a composite air inlet duct. This mock-up tool was created with inspiration drawn from the NASA X-59 experimental supersonic aircraft. This study proves that printed composite tooling can be successfully created and used in autoclave applications. In fact, the tools and the parts that we use in this study are actually here with us today. And a new set of tools are actually being created as we speak. We want to explain the important steps needed in being successful with this process, from how we achieve quality LSAM prints to correctly compensating for anisotropic CTE and other shape changes that happen during the autoclave curing cycle. And it's also important to understand and compensate for pre-preg material spring, which happens on the layup material itself during its curing process. I would like to also mention that the study shows that LSAM printed tools have excellent shape stability after multiple autoclave cycles, showing that longevity can be expected. So with all these factors considered and understood, we can create first-time right printed tooling that has vacuum integrity directly off the machine and produces dimensionally correct finished parts. So what's required to do this? The key to successfully creating autoclave tooling starts with Thermwood's LSAM, which delivers superior print consistency, provides dynamic control of print temperatures, and has the large-scale focused slicing software needed for large-scale format. And then we finish this off with the confidence delivered through predictive simulations via the Composites Manufacturing and Simulation Center at Purdue University. So let's explore how LSAM produces superior print consistency. First, the LSAM is the only machine equipped with Thermwood's patented melt core system for processing materials. This melt core is designed for high output deposition rates to produce large, consistent bead sizes. With our standard melt core producing over 200 pounds an hour, or about 91 kilograms per hour, and our optional larger core producing over 500 pounds per hour, or about 227 kilograms an hour. It utilizes PID heater control to precisely maintain processing temperatures up to 450 C. The heart of this melt core system combines a custom industrial extruder, a polymer melt pump system, and a temperature-controlled compression following wheel. This combination produces the most accurate and consistent beads possible, resulting in superior bond between print layers and the best possible solidity between neighboring beads. So let's break down these three key components. First, the melt core's extruder screw and melt pump system work in complete unison to provide the most consistent and precise material output possible. In large-scale 3D printing, the extruder screw must change speeds constantly. So this custom patented extruder screw design provides a more consistent melt temperature across these changing speeds. Also, it is known that an extruder alone will not produce a consistent material output due to extruder surging, especially at high output rates. So our extruder screw's only job is to keep a positive displacement melt pump system fed. And then the, excuse me, I need a drink. Been doing a lot of talking, I apologize. So the extruder screw will feed the positive displacement melt pump, and the melt pump's servo-driven melt pump will precisely deliver that material to the nozzle. This eliminates the problem of extruder surging. Excuse me. This eliminates the problem of extruder surging and produces the most accurate and consistent beads possible. And another added benefit is that the extruder screw does not need to be changed when switching to different materials. And last and certainly not least, the compression following wheel. An important factor to understand is that unlike other systems, the melt core delivers material to the nozzle, but the patented compression following wheel finishes the bead's final shape and dimension. And this provides an all-important active bead compaction. The nozzle tip is actually slightly above the finished bead height, which prevents the nozzle from needing to drag through the material to create the final bead shape. This prevents excessive material buildup that can be detrimental to the surface quality of your print. This is especially problematic with high temperature materials. The compression following wheel is temperature controlled, but only to prevent polymer affinity, which is the material wanting to stick to the wheel. It's actually quite hot during the printing process. A study performed by a group at the LSAM Research Laboratory further emphasizes the benefits of this active bead compaction. Bead compaction aids in the removal of inner bead voids. It improves the consistency in the printed composite microstructure, which also includes repeatable fiber orientation. It enhances interlayer bonding and provides the best results for lateral bead-to-bead solidity. You can't achieve quality prints if you can't hold the part successfully during the entire print process. And holding parts is a little trickier and maybe a little more important in the large-scale world. So LSAM solves this issue with its patented beadboard print substrate. It provides a strong initial tack, and then the heat from the initial contact allows the special surface to float with the part while it cools and shrinks. Then after the initial layers cool, it holds strong through the entire print process. This prevents stresses that can build in other print substrates. In fact, it actually holds well enough that initial machining operations can be done while still attached to the board. And of course, when ready, they can be removed with just a few simple everyday tools. They are reusable and repairable. Let me also mention that LSAM has a wide variety of print-ready materials that are ready to use. Using any of these materials is essentially a simple one-click activation to apply all the parameters needed to run that polymer. And because of our fixed displacement metering, these material configuration files can be confidently shared amongst all LSAM machines. And it also has automatic routines to load, empty, and purge and clean materials from the system, with on-screen instructions to guide the user through every operation. Excuse me. Now let's explore how the LSAM controls print temperatures. Achieving and maintaining optimal layer temperature is extremely important. If you print too hot or too cold, you will experience various problems, such as weak bonding between layers or excessive part deformation. We must allow enough time for the printed polymer to cool to the ideal temperature range before printing that next layer. So layer time control, a patented technology built directly into the control system of the LSAM, automatically controls the time spent on each layer by adjusting the print speed. This is dynamically handled at the control in real time and ensures that the print is staying at the optimal temperature. And should conditions change, layer time can be immediately adjusted, all while the machine is printing. Maintaining this temperature range results in better and more consistent fusion between layers. Next, let's explore LSAM's large-scale focused slicing software. Producing superior prints requires slicing software suitable for large-scale additive. So Thermwood developed LSAM Print 3D, which understands all the print characteristics of the LSAM. It has all the typical features of traditional slicing software, plus loaded with unique custom features specifically needed for the large-scale additive world. A notable plus is that it creates slicing programs from real CAD data formats, such as solids, surfaces, and sheet bodies. So there's no need to create a deteriorated STL file just to create a print program. LSAM Print 3D has been used to create well over 100 technical demonstrations for LSAM customers. not to mention our own printing and testing. And there have been countless programs created by LSAM owners as well. This experience has driven the features in LSAM Print 3D, and it has been continually refined for over 8 years now. This has resulted in unique, invaluable, patented features targeted for the LSAM and large-scale additive. So at this time, I'd like to pass the program over to Dr. Eduardo BAROCIO to talk about the research laboratory and predictive simulations. Thanks.
All right, wonderful. Thank you, Scott. Well, it's a pleasure to be here today and share a little bit of the scope of the LSAM Research Laboratory at Purdue. So our overarching goal is to enhance the confidence on this large-scale additive technology through predictive simulation that has been developed on a strong scientific foundation and avoid, empirical try and error approaches. So we can get the tools printed and machined right the first time. So we bring a lot of expertise in modeling and simulation of composite manufacturing, characterization of composite materials, and we have a particular tool or virtual twin for this process called Additive 3D. So just to walk you really briefly through the characteristics of Additive 3D, so we basically replicate the process of laying down material bit by bit by activating elements in a finite element mesh while solving a wide range of physics. And what we also enable with Additive 3D is not only to predict the outcome of a print process, such as deformation, stresses, but also to investigate the performance of the as manufactured shape. In the context of autoclave tooling, like the example that is currently being printed, or these other tools here, the performance might be in the context of shape change. Okay, so we're printing with an isotropic material that results into more complex shape changes than just traditional isotropic material. Just to dive a little bit more into this technology of Additive 3D, so we have two key inputs. One is the material card, and the other one is the machine card. So the machine card captures all the effects of flow in the fiber orientation of the printed bead. It also captures interactions of the printed material with the ambient inside the printer, as well as with substrate. That informs the material card. So the material card contains a wide range of material properties that are required to describe different phenomena that occur as the material goes from the melt state, coming out of the nozzle, and cools down to the ambient temperature. Those material machine cards inform the process simulation first, where we can predict, the temperature history, interlayer bonding, the degree of crystallinity if we are printing with a semicrystalline polymer, residual stresses, deformation, whether the part is going to come off from the substrate, and be able to iterate virtually before we go and spend energy, material, and time to find that out experimentally. But then we can, as mentioned before, we can take that information and investigate the performance characteristics of the as manufactured shape. And that means considering stresses that might develop through the print process, as well as the local material orientation and anisotropy of the printed material. So this particular example that we are featuring today, we use Additive 3D and similar technologies for autoclave processing to first predict the shape change of the composite laminate that will result from the cure process. So we predict the shape change of that. We compensated for the shape change of the laminate. Then we designed a LSAM tool. We predicted the shape change of the tool and compensate for that. And then we did the fully coupled simulation to predict the shape change of both the part molded on the printed tool and be able to verify that we are producing the desired composite geometry. Now just to give you a brief glimpse of an example of simulation prediction. So to simulate the print process of the part that is going on right now, we need three key inputs. One is the machine code, the same machine code that is used to drive the physical system, the machine card, and the material card. And as outputs, we can predict residual stresses, deformation, temperature, to name a few. So here we're looking on the left-hand side, the evolution of temperature throughout the entire process. So it's a highly non-isothermal process. We see temperature gradients developing along the height of the part, but also across the thickness of the part. At the middle, we're looking at the stresses in the layer stacking direction. Okay, those stresses that will drive the lamination when the lamination is likely. In this case, it's not a problem. But then on the far right-hand side, we're looking at the deformation in the y direction. So you will notice that this actually tool springs in to some degree, and it's something we can predict and compensate for. So looking at this, again, this particular set of tools that we have demonstrated, we also did a shape stability study where we made our layups, composite layups on the surface of the tool. We cure them in an autoclave at 180 Celsius. And after each autoclave cycle, we laser scan the surface and carry out a deviation analysis to look at the shape stability over multiple autoclave cycles. So as you can see here in this plot, most of the deviations that we observe after multiple cycles is fairly stable and is within the range of less than 100 microns of changes. So we developed this technology at Purdue University, and we work a lot with industry with the goal primarily of enhancing the confidence in this technology. So we provide access to Additive 3D through an industrial consortium, along with print demonstrations and technology demonstrations for the LSAM system. We provide quarterly webinars that are focused on addressing practical problems posed by members, but providing solutions that are grounded on scientific understanding of the process. And that last but not least important, we also provide general support, technical support around Additive 3D or the LSAM technology in general. And I would like to just wrap up our presentation just to summarize, the 4 key elements of the LSAM technology that we covered today. So we first look at the melt core and key patented technologies from Thermwood, like the roller, that provide superior print consistency, which is important to get reproducible results and to get predictable results on the other side of the print process. We also look at the dynamic control of the print temperature that basically provides uniformity and process control that is really unique, and also the large-scale focus slicing software, which on top of the regular features you always see in a slicer, it also allows you to develop a lot of custom toolpaths. And the last but not least important, all the confidence that we provide to this technology area through predictive simulations. And with this, we'll be happy to take any questions that you might have.
Any questions?
Any questions from the audience? Feel free. Okay, gentlemen, I have a couple questions for you. For Scott, what is the typical print bead size on an LSAM?
The typical print bead size is 0.83 by 0.2 thick, which is 21 millimeters by 5 millimeters. The LSAM is capable of printing pretty much any bead size you need, but that's the optimal size for creating and keeping the heat retention necessary to create the quality prints for autoclave tooling and items of that nature.
Okay. Eduardo, what kind of experimental validation has been done for Additive 3D?
Yeah, so we've done extensive experimental validation at different stages of the simulation. So for example, every time we develop a new material card, we do extensive validation. We do blind predictions, compare basically predictions for temperature, crystallinity, semicrystalline polymers, deformation. And if something doesn't match, we don't go and tweak the models. We'd rather go revisit the fidelity in the material models that we use and augment that fidelity to truly provide a predictive tool.
Okay, great. Scott, can you tell us, somebody has mentioned, are the printing fumes a problem with the LSAM?
No, actually every machine that we build has built-in fume extraction. On this particular model, it's actually built in underneath the gantry. So while it's printing, it's pulling those fumes through specifically formulated carbon filters and sweetens it and puts it back into the air.
Okay. Fantastic. How about Eduardo? What physics are captured in additive 3D?
So there's a wide range of physics that we capture, including anisotropic heat transfer. There is also there could be a compactor that is actively cooled down to prevent the material from sticking to the compactor. So there is heat losses in that. So we capture the reheat that is removed by the compactor. We capture convective and radiative heat losses that come from the evolving geometries. And also we have particular correlation expressions to treat the different convection conditions that are part my experience in the interior versus exterior. We consider also anisotropic shrinkage due to not only the coefficient of thermal expansion, but also due to crystallization in semicrystalline polymers. We use an anisotropic viscoelastic material formulation for the material behavior. We use a diffusion-based approach to predict interlayer bonding at every point in a print. And also we have different modeling approaches for the substrates. Depending on the type of substrate the part is printed, there are different modeling approaches that we have available for that.
Thank you. Scott, one more question for you. What type of industries are LSAMs being sold into?
Quite a few. We've sold into, of course, aerospace, architecture, the foundry industry, automotive, just to name a few.
Okay, and one last question. How many different materials have been used on LSAMs?
Currently, to date, there's over 40 materials that we've used on the LSAM. Those are available to every LSAM owner, and as time goes on, we test and more become available. And our users have the ability to create their own, and if they choose, they can provide that to other users as well.
Okay. Thank you so much, gentlemen, for this lively presentation. And if you would like to ask them further questions, don't hesitate to come around the machine. You've got worldwide experts here, so it's a great opportunity to learn all about this technology. Ladies and gentlemen, this concludes the live demo area for this year's JEC. But the good news is that we will be back again next year for JEC World 2025, March 4th through 6th, and we will have an even bigger space. And for this year's edition, we would love to thank so much our partners, Thermwood, Composites One Aerovac, MVP, and Rock Tool for all of the fantastic presentations and demonstrations that they've given during these 3 days. Thank you so much, ladies and gentlemen, for coming, and enjoy your afternoon at the show.